All right, so let's work through example 5. We have f of x equals 3x squared plus x plus 2, and we want to do all the same stuff. Is it concave up or down? Where's the vertex? What's the axis of symmetry? Where is the y-intercept? Where are the x-intercepts, if there are any? Find the domain and range. Where is it increasing? Where is it decreasing? Where is it positive? Where is it negative? All the same stuff. Okay, so hopefully this is kind of old hat by now, so I'll actually pause right here, letting you go ahead and do this example on your own. Okay, so hopefully you would have found something different this time compared to other times. Let's see what happens. The number multiplying x squared is 3, so that's A. The number multiplying x is 1, so that's B. And the number hanging off by itself is C, so that's 2. Okay. Before moving on, just to illustrate something, if this was, say, the following, 3x squared plus 2, what's A? Well, A is the number multiplying x squared, it'd be 3. What's B? B is the number multiplying x, and it's not there. This would be where B is equal to 0. Similarly, if it was 3x squared plus x, well, then you would have C equals 0. There isn't any number hanging off by itself. Every example the book has done had a non-zero value for A, B, and C. I just want to show you that it's okay for B to be 0 or C to be 0, as long as A isn't. If A is 0, if you don't have any x squareds, you just don't have a quadratic function. Okay. In this example, A is 3, so we are concave up. That means we're going to have a minimum somewhere. Let's find the vertex. Where is this minimum going to be? Well, same formula, negative b over 2a, which gives us negative 1/6. Oh no, it's a fraction. Let's all cry and scream. No, fractions are fine. How do I find the y-coordinate? I have to plug negative 1/6 into this function, which isn't that big of a deal. Something tells me the book is just going to give us, oh no, they actually do it. Okay, so what is negative 1/6 squared? Well, negative 1/6 squared, so I'm just going to do the work up here, is 1 over 36 plus negative 1/6 plus 2. Let's simplify. What's 3 times 1 over 36? I cancel out the 3 and I get 1/12 minus 1/6 plus 2. Now I have a bunch of adding and subtracting of fractions. I find a common denominator. My denominators, respectively, are 12, 6, and 1. So the common denominator is 12. So I'd have 1/12 minus 2/12 plus 24/12. Now that everything has the same denominator of 12, I can just do 1 minus 2 plus 24 and get out 23 over 12. So there's the y-coordinate of the vertex. So the vertex is at negative 1/6, comma, 23 over 12. And the vertex, remember, gives you the x value for the axis of symmetry. X equals negative 1/6. Okay. To compute the y-intercept, just plug in x equals 0, and you'll quickly get out y equals 2. And then the question becomes, what about x-intercepts? So we look at the discriminant, b squared minus 4ac, and we find 1 squared minus 4 times 3 times 2, which is negative. So what happens when the discriminant is negative? There are no x-intercepts, which we could also see because we already knew the vertex was here. Okay, we computed this. We also know that it is concave up, right? So before we graph anything at all, I'll end up erasing this in a second. Okay, we know the vertex is here. So the vertex has a positive y value. Specifically, it's 23/12. And it's concave up. So I have to draw something like this. It's never going to have any intercepts. This is what a negative discriminant corresponds to. Either a positive vertex and concave up, or a negative vertex and concave down. That's what's going to happen when you have a discriminant of 0. Okay. So using, we also know our axis of symmetry was x equals 1/6, negative 1/6. We knew our intercept was 0, 2. So this is 1/6 of a unit to the right of the axis of symmetry. From x equals minus 1/6, I would have to add 1/6 to get to 0. So I can exploit symmetry and subtract 1/6. And negative 1/6 minus another 6 is going to be negative 1/3. And since this was at a height of y equals 2, so is this point here. So using some symmetry, we can get another point. Okay, the domain is all real numbers. Okay, quadratic functions always have domain all real numbers. The range, since this is concave up, starts at the minimum and then goes to infinity. Where is it increasing and decreasing? Well, it is decreasing until it hits its minimum, and then it is increasing from its minimum on. But notice the graph is always positive. Whether the graph is increasing or decreasing, this one is always positive. So it's never negative. Okay. So can we find, so that's that example there. Okay, so now, moving on, suppose I know the vertex and one additional point. Then we can find the quadratic function that gives us the vertex and one additional point. Thinking back to linear functions, remember that if you know 2 points on a line, you can determine the line. You can find its slope, and then you can use point-slope form, and you're good. For a quadratic function, 2 points is actually usually not enough information. It's only enough information if one of those points is the vertex. So I want to stress, this is not saying using 2 points. It's saying a vertex and one other point. It's very specifically the vertex of the parabola and one other point. Okay. So how are we going to do it? So suppose I have a quadratic function, and here's the vertex, -3, -7, and specifically the y-intercept is 2. So we know h is -3 and k is -7 because we were given the vertex. So here is vertex form for a parabola, and I just go ahead and plug in h is -3 and y is 7. Notice we have an x minus -3. We're just going to call that x plus 3. So the only thing missing that we don't know is this value of a. That's the only thing in vertex form for the parabola that we don't know yet. What we do know, however, is that the y-intercept is 2. And that tells me that if x is 0, y is 2. So we're going to use x equals 0 and y equals 2 right here to determine the value of a. So here was what we have so far for vertex form. I'm going to let x equals 0 and y equals 2. What's 3 squared? 3 squared is 9. And notice what we have now. 2 equals 9a minus 7. I can solve that for a and get a equals 1. And now I have, this remember here was a, which is just 1. If you want, you can expand this out and cancel some stuff off and get that. Or you can leave it in vertex form. Just like I think point-slope form is a perfectly good expression for a line, vertex form is a perfectly good expression for a parabola. So if you want, you can just leave it there. Okay, here's the graph. Let's do another example like that. Determine whether the quadratic function has a maximum or a minimum, and then find it. How do I know whether a quadratic function, a parabola, has a max or a min? It's whether it is concave up or concave down. Okay? So since this is concave up, it has a minimum. What is that minimum value is exactly the same question as finding the vertex. So find the vertex. H, or the x-coordinate, is -b over 2a, which we compute to be 3. And then finally, the minimum value is the corresponding y-coordinate. So plug 3 into the function and get out -12. Okay. So finding a parabola given a vertex and one other point, using the vertex that's given in vertex form, the only thing that remains is to find the a, and you use your other point to compute a. And then finding the max or min of a parabola is really just asking, find the vertex, and that's something we've already done several times. Okay, so another example. Okay, a water balloon is launched from 100 feet above ground at an inclination of 45 degrees. So we start 100 feet above the ground, and I launch it in this direction, so the balloon is going to go up and come back down. And here is the corresponding equation of motion. -32x squared over 100 squared plus x plus 100. Why write 100 squared and not just 10,000? It'll just make some computations later easier. Find the maximum height. So how high will this water balloon go? And also, how far from the base of the stadium will the balloon be when it actually hits the ground? So what we're trying to find is, what is the highest height? So find the vertex and find its height, its y-coordinate. And then, what is the corresponding x-coordinate of where I actually hit the ground? Okay, so I'll pause, try to find the y-coordinate of the vertex, and then try to find an x-intercept. Okay, so this is not fundamentally more difficult than other problems we've done. It just involves some uglier numbers to work with. But the process is exactly the same. So here's the parabola. So to find the maximum height, sure, we'll simplify down that 100 squared. Because a is negative, it is a downward opening parabola. It's concave down. We're looking for a maximum. So we find the corresponding x value, which is just negative b. Notice that b is 1 over 2a, and a is negative 32 over 10,000, which does simplify down to 625 over 4. If you had just used a calculator, you could have gotten out 156.25. There is our x value. But then we need to find the corresponding y value. We would definitely do this with a calculator. So we just have to take that value of x and plug it in. So who wants to square 156.25 by hand? I don't see anyone with their hand up, and I wouldn't want to do it either. But a calculator simplifies this pretty quickly to 178 and an eighth. So there is our maximum height. We started at a height of 100, and we lobbed it up according to the following function, h of t. I think they used x, sorry. H of x is negative 32 over 10,000 x squared plus x plus 100. So what is the highest value? 178 and an eighth feet in the air. The second part of the question was, where does it hit the ground? Which means we need to find where is the height 0, or find the x-intercepts. So we just need to apply the quadratic formula, honestly. We compute the discriminant, b squared minus 4ac. Notice that a is quite small, which is 2.28. Okay, so it's positive, so it has 2 x-intercepts. So we're going to apply the quadratic formula. B is 1, b squared minus 4ac we just computed to be 2.28, and then a is that very small negative number down there. Again, not going to do this by hand, but a calculator tells us 2 possible answers. Negative 1 plus root 2.28 over all of this gives me one value, and negative 1 minus root 2.28 over all that gives me another. Which one of these uses the plus and uses the minus? Okay, a lot of people might look at this and say, well, I happen to know, just from looking at the picture, that I don't want a negative value of x. I want a positive value of x. So they say, I must want the plus. And then they'll get out this answer, and they'll say, Professor, my calculator's broken. This doesn't make any sense. And I'll kind of smile, look at them, and I'll say, I'm sorry, you need to know how to use your own calculator. Okay. Because the denominator is negative, in order to get out a positive x value, I actually want the numerator to also be negative. So actually, it's the minus root 2.28 that gives me the positive answer here. Okay, so in any case, you can just compute both and say the x value that's negative doesn't make much sense. I have a positive x value of 392 feet. So, whoops, sorry. The picture looked kind of like this. That is a terrible axis. Let me start over. That's not much better. Let me clear out all of my bad drawings and hope that I can start with a slightly better one. Barely. Okay. So we started at a height of 100, and then the water balloon did something like this. So what does this represent, this negative value that we're discarding, if you had drawn the parabola to keep going like this? So this was, I'll just write the function again, h of t equals, oh gosh, what was it? It was like 32, negative 32 over 100 squared t squared plus t plus 100. Okay. What's the domain of this function? Okay, it wasn't asked by the book, but I want to ask it. So we have found that this is about 392, 0. This is 0, 100. The domain is actually just from 0 to about 392.18. Because it doesn't make any sense in this particular problem to talk about these x values over here, because the balloon started at this x value. And once the balloon hits the ground, it does not traverse into the earth and start falling through to the core. Okay? It hits the ground and it stops. So because this was modeling a real-world scenario, the domain is not necessarily the same as what's the domain of this function overall. In this problem, the domain would actually be capped at both ends. It starts at 0, which is where the balloon is launched, and it ends at 392.18, which is when it hits the ground. Okay, so that's the end of section 3.3. So come on back later and start going through section 3.4. We'll keep talking about quadratic functions.